Welcome to a lesson with Dr. Powell. Let's look at an example of computing a surface integral. That is, we're going to be integrating a vector field. Now, this is a constant vector field. Notice that it doesn't depend on x, y, z. It's a constant in relation to them. So we're going to integrate this vector or vector field, if you will, defined at every single point in space here over the surface, this surface that I've drawn. And we're going to say that this is the top half of a unit sphere, just the top half part. So let's let S be that surface. Then we're looking at the components here of this vector, 1, and then we put what's orthogonal to x, which is dy dz, but we put it in the right order using this symbol to denote that for orientation. And then plus 0 dz dx plus 1 dx dy. Okay, now that's just 0, so that's gone. So we're just looking at that. Now it'd be nice to write all of this in terms of x and y. Here, this is z, so we need to find a relationship between z and x and y. All right, so keeping in Cartesian coordinates, the unit sphere is x squared plus y squared plus z squared is equal to 1. Think about a function of 3 variable input equaling this, and then we set it equal to 1. That would give us a level surface of this function. So if we stay on that level surface, any run inside that level surface or along it tangential to it should cause a rise of this outer function to be 0. And we can see that in a chain rule type calculation so we can do this implicitly. Take the derivative of this function, 2x, 2y, 2z, so it's gradient. And then let's just suppose we're gonna take the derivative of this with respect to x, say, and let's let z depend on x and y, but y be independent of x. So you can think the derivative of x with respect to x is 1. The derivative of y with respect to x is 0, since they're independent of each other. But we're going to say z depends on xy via this equation on this level surface. So there's going to be some dependency. So I'll just write out the derivative of z with respect to x, and to impose the condition that this is on the level surface for this dependency. So how much is this changing in this direction, so that I'm on the surface still? We just put a 0 here, meaning that if this is the run, then and if this is the run right here, then we're going to expect a 0 rise of that function. Okay, so we need to compute this via this, and if we do that via this dot product, you'll notice we have 2x plus 2z x is equal to 0, and then we're going to get negative x over z. And then by symmetry, we have the partial of z with respect to y is negative y over z. So if we're computing dz as the rise of the z function, we take the derivative of z, which is, well, here's the partials right here, so it's just that. Then we put in the run, which is dx dy, and just take a dot product. So we see exactly what dz is, and we can write this out right here. This is dy wedge with, it looks like negative x over z dx minus y over z dy. Okay, now when we wedge in, so this is an area operator. Dy wedge with dy is just 0. So we're just looking at this. This is like a scalar, it comes out front. But the dy wedge with dx is in the wrong order. So we switch it, dx dy, and we put a negative x over z. And just remember, so the order of this that we see here, dy dx, I mean, this is like we're seeing y counterclockwise from x as we go, but if we look at it in the way that we're used to, y is clockwise from x. So that means we must be looking at it backwards or from the other side, which means the area must be negative of what it is when we do dx dy. That's why so when we switch it, we actually need to change the sign. So that negative, so even though this negative xz comes out front, when we switch the dy and dx to this side, we got to change signs. So we apply a negative. We already have a negative, so it becomes positive there. So it looks like this is what we're integrating from this part. From this part, it's just a 1. Okay, so it looks like we're doing x over z plus 1. All right, x over z plus 1 dx dy, and we're doing over this region. Now we've changed it to x and y coordinates. The unit sphere in there is just a circle. And so we could just convert this to polar coordinates and do r dr d theta, go from 0 to 1, 0 to 2 pi, and think about, so x is our cosine theta, and z is actually square root of 1 minus r squared. Why is that? Because the equation of the unit sphere up here can be thought of in cylindrical coordinates as z is equal to positive square root, so the top part of quantity 1 minus r squared, because you're kind of thinking about 1 minus x squared minus y squared when you solve for z squared in just the regular equation here in Cartesian coordinates, take a square root. And think of this as factor out the negative, x squared plus y squared is r squared. Okay, so using that idea, and we can convert it to polar coordinates. And let's see here, 1 minus r squared, and then we have a plus 1 right here. Okay, and times r. Now, keep in mind, I mean, we could just split this over both parts here. And if we integrate it over just the 1 with the dx dy over that region, that's the same thing as finding the area of that circle, which we know is pi. So really, we can say when we integrate this part, we're going to get pi. And so we just add that to the result of what we do when we integrate this part. So we really could just ignore this plus 1 here and just say the result is pi plus this integral here. Okay, now we could do a few things here, but actually there's a faster way to do this. I mean, we could do a trig substitution, and that's fine to do that in this case. But notice that cosine theta is a constant with respect to the r integral. So you could factor the cosine theta out. And so put a cosine theta here. Notice, so it's cosine theta times the output of some integral of this integral, which is just going to be a number, right? It's just going to be some number. So you're going to have a number times cosine. Well, what's the integral of cosine from 0 to 2 pi? Well, that's just 0. So this whole integral is just 0. So we have pi plus 0, which is just pi. So it looks like the surface integral that we were after, the result was just pi. Now this should make sense that the integral from coming from this part should just be 0 if we have a constant vector, because thinking about projections here, if we go on to the y's, so the yz kind of cuts this in half. Notice how this shape is symmetric on either side of this. And if we have a vector, just a single vector going through this, see, what is it? It's 1, 0, 1. So in the x, it's out 1, z, it's out 1. So it's like this. Okay. So we have same vector going out here, here, and here, here. And what the surface integral does, just at least differentially, it kind of just sees what kind of flow is going through this surface. So you have a flow this way, but so if you have a flow this way over here, on this side, on the opposite, kind of just thinking about in terms of just in relation to this direction here, it's going to be so on this side versus the other side of this this half, we're going to be looking at a negative on this side versus this side, kind of on because of different orientations, kind of facing this way versus this way. So everything that happens here is going to, the same thing's going to happen over here negatively, and things are going to cancel and be 0. And maybe we can see this more later as we keep going through videos. But here, at least in this calculation, we see that this is 0. Now, we could practice this, this trigonometric integral if we want, and maybe we'll just put that on real quick. So, I mean, it's unnecessary, but we'll just work through it. So we got, so that's just r squared over, what is r squared? Dr. So just the calculation of this integral. Well, if we think about a triangle, if we think about, let's see, cosine theta. Actually, let's do t and sine t, and that angle's t. Then if r is equal to this, then cosine is equal to 1 minus r squared. So we can think of this whole bottom as being cosine t. And then the top is being sine squared t. And then think of dr, the derivative of sine, to be cosine t and then dt. So really this just changes to this, but as sine goes from 0 to 1, because that's what r is, going from 0 to 1, t goes from 0 to pi halves. And those cancel. So you're just looking at this integral, we use an identity. And then we take an antiderivative, 1/2. So what is that? That's 1/2 t. And then the antiderivative over, and then we take the antiderivative of that, which is minus sine 2t over 4. And then we're going from 0 to pi halves. Notice that this part right here turns into pi fourths, the calculation. This part actually turns into 0. And that's because, think about it, sine of pi and sine of 0 both 0 here in the calculation. So we just get pi fourths. So this constant that we didn't really care about in the end, because we were just multiplying by 0, was pi fourths. Thanks for watching.